Have you ever wondered how some things just find their balance? You know, like the fizz in your soda can, or even the oxygen in your own blood. Well, there's this incredible principle at work called chemical equilibrium. And today, we're going to totally demystify this amazing balancing act that nature pulls off all the time.
Okay, so to really get our heads around this, let's step out of the chemistry lab for a second and imagine we're at the beach. Picture it. You've got people soaking up the sun on the sand and others cooling off in the water. Now, when the sunbathers get a little too toasty, what do? They head for a swim. And when the swimmers get tired, they come back to the sand to chill out.
So what if, and this is the key part, what if for every single person who gets hot and jumps in the water, another person gets tired and comes out? The total number of people on the sand and in the water, it stays exactly the same, right? Even though people are constantly moving back and forth. That, right there, is the big idea behind equilibrium. It's a perfect dynamic balance.
All right, so that whole back and forth thing we just talked about on the beach, that's everything. Because in chemistry, it turns out, not all reactions are a one-way street. Nope. A lot of them can go forward and then just turn right around and go in reverse.
And this has a name, of course. It's called a reversible reaction. I mean, we usually think of a reaction as A plus B makes C, and that's the end of it. But here, C can actually decide, you know what? I'm going to go back to being A and B. It's pretty cool.
So to show this kind of two-way chemical traffic, we ditched the normal one-way arrow you're used to seeing. Instead, we use this special symbol, a pair of arrows pointing in opposite directions. It's basically a little secret code for chemists that says, hey, this reaction goes both ways and it's headed for that perfect state of balance.
And that state of balance, well, that's what we call chemical equilibrium. But here's the number one thing to get right, a point where a lot of people trip up. It's all about the rates of the reaction, not the amounts. It doesn't mean you have the same amount of stuff on both sides. It means the speed at which you're going forward is the exact same as the speed you're going backward.
Yeah, it's so easy to think that once a reaction hits equilibrium, it's just stopped, done. But that's not it at all. It's actually the total opposite. The reaction is still going like crazy in both directions, forward and reverse, just at the same rate. Think of it like a beehive. It might look still from a distance, but inside it's a constant buzz of activity, just perfectly balanced.
Okay, so we've got a handle on what equilibrium is, but how does a reaction actually get there? What's the journey like? Let's check out a really classic example to see it happen right before our eyes.
So imagine we've got this sealed glass tube. Inside, there's a totally colorless gas, dinitrogen tetroxide. Now, when the reaction starts, this gas begins to break down into something else, nitrogen dioxide, which just so happens to be a brown gas. So this is awesome because we can literally watch the reaction happen as the tube starts to get darker and darker. So let's walk through this step by step. Right at the beginning, it's all one-way traffic, right? The forward reaction is going full throttle, making more and more of that brown gas. But as that brown gas, the product, starts to build up, something new starts happening. The reverse reaction slowly kicks into gear. Meanwhile, the original colorless gas is getting used up, which means the forward reaction starts to slow down. So you see what's happening? One speed is going down, the other is going up, until, boom, they meet in the middle and the rates become equal.
I love this analogy. Think of it like two runners on a track. The forward reaction rate shoots out of the starting blocks, just sprinting, but it starts to get tired and slow down. The reverse reaction rate, on the other hand, starts from a complete standstill and gradually picks up speed. And equilibrium? That's the exact moment they're running side by side at the exact same pace. Perfectly matched. So let's wrap this part up. What does equilibrium actually look like? Well, first, the forward rate equals the reverse rate. That's the big one. And because of that, things like the color of the gas stop changing. The amounts, the concentrations of both the reactants and the products become constant. But the most important part, don't ever forget that underneath it all, that system is still dynamic. It's buzzing with activity.
Okay, we've covered the what and the how of equilibrium. But that leaves the really big question, right? The why. I mean, why do reactions even bother trying to find this balance point? What's the point? Well, the answer, as it so often is in science, comes down to energy.
Yeah, this isn't just some random accident. It turns out nature has this fundamental drive to push systems toward this state of balance. The easiest way to picture it is to think of a ball on a hill. Where's it going to end up? It's always going to roll down and settle at the lowest possible point, right? It won't stop halfway up.
Well, for a chemical reaction, that lowest point on the hill isn't always turning everything into products, and it's not staying as reactants either. It's that unique, specific mix of both that you find at equilibrium. That is the most stable, most energetically comfortable place for the system to be. You could almost say it's chemically relaxed. And in chemistry, we actually have a way to measure that lowest point. It's called free energy. You can basically think of it as the available energy a system has to get something done, and a reaction will keep going as long as it's giving off that free energy. But right at equilibrium, the change in that free energy, what scientists call delta G, hits zero. The system has no more drive to change. It's found its happy place, its point of ultimate stability.
Now, I know this might all sound a little abstract, like something you'd only see in a chemistry lab. But trust me, once you know what you're looking for, you'll start to see equilibrium everywhere. It's all around us, and it's even happening inside your body right now.
Think about a simple, sealed jar with a little bit of water in it. Water molecules are always evaporating into a gas, and at the same time, the gas molecules are condensing back into a liquid. At equilibrium, those two rates are perfectly matched. But here's where it gets really important. The way your body transports carbon dioxide in your blood, that depends on a whole series of these reversible reactions. That equilibrium is what keeps the pH of your blood in a super tight, perfectly balanced range, and that is absolutely critical to keeping you alive. So look, if there's just one thing you take away from all this, please let it be this. Equilibrium is not a static finish line. It's not the end of the road for a reaction. It's an active, dynamic, constant state of balance. It's like a perpetual dance between the forward and reverse reactions.
And that leads to a really fascinating question, doesn't it? If equilibrium is nature's preferred state of being, its happy place, what happens when we mess with it? What happens if we come along and knock it off balance? You know, if we suddenly dump in more reactants or crank up the temperature, how does the system fight back? Well, understanding that, that's where things get really interesting.